Good day, everyone, and you are welcome once again to Ojibra Academy channel. I got a DM as usual to make video on Hess Law in chemistry. Now, before I make the video, I like to make announcement that we'll be making videos on subjects like chemistry, physics, biology, including some part of biochemistry as well. But anything that has to do with mathematics, we are still considering videos on it. I've not concluded yet because I got comments to make videos on loci in mathematics, on constructions in mathematics, and other topics like that I got comment about. So I'm just using this medium to announce to our viewers and our followers that we'll be making videos on basically for now, predominantly chemistry, physics, biology, and some part of biochemistry. Videos of mathematics will come later. So the video on S law that I promised that I'm going to make. S law is a subtopic in thermodynamics in chemistry. S law. And in S law, basically, what we are interested in doing is to measure the heat of reaction, the heat content that accompanies a particular reaction. But then, S law is there for us to measure the heat of reaction of a reaction that we cannot measure its heat content holistically. But we can represent that reaction in other several steps. That is, if you have a reaction, then in that reaction, the heat of content is not possible for us to measure directly. If you have other parts of the reaction that we can break down and measure their own heat, the cumulative heat of other steps that we break down will give us the original heat content of the main reaction we want to calculate. For instance, now if you have A plus 2B to give 3C plus D, for instance, if this is a reaction, supposedly, if you have a reaction like this, so to say, and the heat of reaction is not, the enthalpy of this reaction is not possible for us to measure directly, then we can have some other reactions that we can add together to get this main reaction. For instance, we have C to give maybe half of D. Then we have number 2, we have A plus B to give C. Now, if you look at these two reactions, we have all the content of this is the main reaction that we are interested in measuring its enthalpy, but we can't measure it directly. But we have these other two reactions in which we can combine together to get the first reaction, like that. But if you look at it very well, you will see that we have C here at the reactant side. We will have been given the change in H, that okay, change in H of this is probably plus 10 kilojoule per mole, or change in H of this is minus 30 kilojoule per mole. This is just an hypothetical reaction. I'll still give a particular reaction to solve this. Now, if you look at this first reaction, we have D there, which we have in the main reaction. We have C there, which we have in the main reaction. We have A and B, which we also have in the main reaction, and we have C that we have here. But if you look at it properly, C here is at the reactant side. While C in the main reaction is at the product side. A and B, they are at the reactant side. C is also at the product side. We can use this second reaction directly without touching it. But this first reaction, we must do something to it because the reactant and the product are not exactly where they are supposed to be in relative to the main reaction. So that is where people get confused when calculating questions on S law, because the other reactions, the other steps reaction will not be represented exactly the way we have it in the main reaction. So it means we have to do some things to the other reaction to make it suit our main reaction that we're interested in calculating its enthalpy. Now look at this question. So considering an equation like this, you can see we're given these three equations. These three equations are like additive equation for the main equation that we have there. We have carbon reacting with oxygen to give ethyne. We have carbon reacting with hydrogen rather to give ethyne. We have carbon burning in oxygen to give carbon oxide. We have hydrogen burning in oxygen to give water. These three reactions, the cumulative results make this last reaction. So it looks like we cannot measure the heat of reaction of the combustion of ethyne directly, but we want to measure from the constituents of this particular reaction. You discover that we have ethyne at the reactant side here. We also have a reaction where we have ethyne in equation 1, but it is not at the reactant side, it's at the product side. We have oxygen at the reactant side, and we have two equations where we also have oxygen at the reactant side. We have CO2 at the product side. We have one equation here where CO2 is at the product side. We have water at the product side. We have water at the product side. It means if we change the formation of these or the orientation of these three stepwise reactions, it's going to finally give us this reaction we want to calculate heat of reaction. So let's go. Now let's take a time as a case study first. Ethyne is at the reactant side here. We have an equation where ethyne is at the product side. So it means we are going to change ethyne from from product to reactant. We flip, we call it flipping. So instead of having the first equation like this, we are going to rearrange as C2H2 gas to give, we are turning reactant to product and product to reactant to give 2C solid plus H2 gas. Now, the effect of that is that our standard heat of formation is plus 226.7 originally. This time around, it will change to minus, changing H will now be equals to, standard heat of formation will be minus 226.7 kilojoule, because we have flipped reaction. We have changed reactant to product, product to reactant. So if the reaction was initially exothermic, it will change to endothermic. If it was initially endothermic, it's going to change to exothermic. So we have our ethyne now, ethyne. Now, another thing that we want to consider is carbon 4 oxide. Carbon 4 oxide here, at the product side here, it is 2. Where at the product side here, it is 1. So it means we are going to just multiply this equation by 2. So we're going to have carbon. We don't need to flip this one because carbon 4 oxide is at the appropriate place. So carbon plus O2 to give CO2 like that. Now, in this equation, we have 2 CO2, but here we have 1. So we have to multiply the equation by 2. So you're going to change to 2C, 2O2, 2CO2. So the heat of standard formation, instead of 393, we're going to multiply 393.5 by 2. So it's going to give us minus 787 kilojoule. We have multiplied everything here by 2 now. Now for the third equation, we're not going to change anything. We're not going to change anything because we have oxygen at the reactant side. In this as well, we have oxygen at the reactant side. We as well have water at the product side. Here we also have water at the product. So we just write like that. We're having H2 gas plus half O2 to give also gas to give H2O. So the standard heat of formation is not going to change. It remains the same thing because we didn't flip and we didn't multiply by any number. 285.8 kilojoule. Now, we don't have more than what we need. In the main equation that we are given, we don't have hydrogen. But in this equation, we don't have hydrogen. But thank God we have hydrogen at opposite side. We have hydrogen here, we have hydrogen here. They can cancel out. The hydrogen here cancel out the hydrogen here. Now, what again cancel out? We should check. Whatever you have that they are the other side of, they are the opposite sides, they can cancel out. Now we have carbon here, we have carbon here. Two carbon, they can cancel out because carbon is not needed in this equation. Two carbon here, we also cancel out the two carbon that we have here. So it means we have our main equation. Now we have at the reactant side of the total equation, we have C2H2, we have C2H2. We have 2O2 plus half O2. If you add 2 plus 1, 2 plus 1 over 2 rather, 1 over 2 and 2, if you add it together, your answer will be 5 over 2, which is what we need here. So it means we are adding all the equations together. So at the end of the day, we're going to have C2H2 gas. When you add the two reactants here, it gives you 5 over 2 O2, also gas, to give, we have 2 CO2 plus H2O, which is what we have in this main equation. Then we can now add all these things together to get our answer. It will now be changing 8 of standard formation is equals to minus 1299 kilojoule. So this is how Hess law works. We are going to add the individual equation you sum it up together for you to get the equation in which you are asked to calculate the heat of reaction. It also shows that even if you break reactions into several other steps, the heat of reaction still remains the same. Thank you, and you're welcome.